And good evening. My name is Steph. Of course, a very loud plane would go overhead right now. My name is Stephanie Sepiol-Mill, and I serve as the Assistant Director of Alumni Communications here at Valparaiso University. We are thrilled to welcome you to the Polar Vortex, Lake Michigan, and Wintry goodness in Valparainsnow, Indiana, the fourth program in a series of Alumni Experts virtual events sponsored by the Office of Alumni Engagement. This evening, I'm joined by University Professor Craig Clark, class of 1991. A longtime snow enthusiast, which, by the way, Dr. Clark, I don't know about that moniker. I could never identify with that. He has been teaching at Valpo since the early 2000s and completed his Ph.D. at Iowa State University in 2007. Thank you so much for taking the time to join us, Professor Clark. Participants, please feel free to use the chat to ask questions of tonight's guest, and we'll get to them throughout the program. This program is also being recorded, so you'll be able to watch a replay on the Valpo Alumni YouTube channel. And as I said in the chat as well, near the end of the program, we will have a little extra time for questions. So if you'd rather save your question to ask it out loud, you can do that too. So I will preface Dr. Clark's presentation with my question, which kind of inspired this program. So the winter of 2021 was seemingly wilder than ever before, affecting more Americans in parts of the country that aren't used to these extended periods of snow, ice, and bitter cold. How do meteorologists, such as yourself, explain these types of anomalies? And maybe are they anomalies?
All right. Well, happy to be here with you to talk about some of these things. The turnout here is really fantastic. I didn't know what to expect when this came out, and Stephanie reached out to me what kind of turnout we would get, but this is a pretty remarkable turnout. And I see a bunch of meteorology program alums in the mix here. So feel free to ask lots of questions via the chat, and if you stump me, I'll just throw it back at my former students and see what they can come up with. So this will mostly be a pretty general talk in terms of the level. I intend this for a fairly broad audience, assuming everyone is somewhat interested at least in the topic, in order to devote some time to it. But I don't want to assume that people know, tons of stuff coming in. But we'll have a little bit of fun as we go through some things. So Stephanie asked me about the polar vortex and how that would relate to wintertime sorts of things after the February, very impressive few weeks of February that we had through much of the country and here in Valpo as well. And as I thought about how I would approach that, it made sense to link it to more broadly some things that influence our weather in the wintertime, especially here in good old Valparaiso, Indiana, which we all, in this group have some connection to currently, or at least in our past. So here's just a quick outline. Why am I so interested in snow? Because I've always loved snow, and then kind of a little bit about the types of snowfall that occur here in Northwest Indiana, and more broadly, kind of the Lake Michigan or Great Lakes region. And then kind of taking a broader view of the large scale patterns that foster snow and cold here, and then how that relates to the polar vortex, which sort of entered the public lexicon back in the very impressive 2013-14 winter. So first, why snow? Why am I so interested in snow? Well, I don't know. When I was a little kid, most little kids like snow, and I grew up in Rolling Prairie, Indiana, which gets a lot of snow relative to Valpo, actually, almost twice as much on average, being closer to the heart of the Indiana lake effect belt. And I happened to be a kid in the late 70s, which featured some really impressive winters in the region. And honestly, Perhaps ironically, I didn't like going to school. And so the fact that I was in a rural school district that canceled school a lot when it snowed probably was part of why I like snow so much. So I just, from really second grade on, I've just always been really interested in snow. I didn't know that my job would have anything to do with it, of course. I'm also interested in the Beatles, and my job doesn't have anything to do with the Beatles. But here you have it. So there's my on the left, a couple of pictures of fun in the snow with my son Jensen. So we have some good times in the snow. And then this is a weather map of a surface weather map up top here of the most awesome snow event that I've ever experienced in my life, or probably ever will experience. This is more broadly called the Cleveland Superbomb Storm, where a system from Texas and an Alberta clipper coming down from Canada effectively merged over Ohio and blew up into this huge storm with incredible winds. And so you had pretty impactful weather from, Chicago to Detroit and beyond. But right in the lake effect belt of Indiana into Southwest Michigan, there was, 2-3 feet of snow instead of just a foot. So it was a really remarkable storm that I've remembered to this day. So what about some general things about snowfall before we get into large scale patterns? Obviously for snow, you need cold air to at least some extent. It does not have to be that cold in the grand scheme of things. It just has to be cold enough. Once it's cold enough, making it colder won't necessarily get you more snow, with some caveats there. You have to have water vapor, right? So it's got to be provided by something. You need to have some water vapor in order to make the snow. So weather systems that come through here with more water vapor have more snowfall potential than others. And then you need to have lift in the atmosphere. You can have cold air and some water vapor in place for a long time and not get meaningful snowfall if you don't have lift in the atmosphere. So there are certain discrete days in which you get lift in the atmosphere, usually from mid-latitude cyclones lumbering through, storms, and then you get the snowfall. And so in our region here in Northwest Indiana, our snow principally comes from two sources. Mid-latitude cyclones, all this stuff with cold fronts and warm fronts and all those lows that traverse through the region in the winter. It's cold enough, give us snow. And then lake effect snow, which is quite a bit different. And so I want to briefly talk about those a little bit more and maybe their temperature sensitivity before moving on. So here's a fun example, or more recent example, of a mid-latitude cyclone that had a tremendous amount of water vapor with it. So in of itself, this low wasn't, anything to write a textbook about. It was a respectively strong low, but it was not otherwise all that remarkable. It didn't generate a lot of wind. It had a decently low central pressure, but again, nothing all that noteworthy, except that the warm sector of the storm had a lot of water vapor from the Gulf of Mexico. This was a water-loaded system. There was a ton of water vapor. What's interesting about this system is it came through and influenced Northwest Indiana and also Chicago, is that it was barely below freezing until, and in fact, a few hours before the precipitation started, our surface temperatures were a little bit above freezing. And this is a sounding that our students took. So some of our meteorology students like working with instrumentation, and we have a sounding system where they can launch balloons and then collect weather data through the troposphere and lower stratosphere. And so this is a plot that the software made after they did a launch on this particular day. And this slopey line right here represents freezing, 0 Celsius. And in the lowest couple of kilometers, which are really critical for precip, it was barely below freezing. In fact, just looking at this sounding, if this system hadn't had pretty good lift with it, we actually would have had cold rain or like kind of a sleety, slushy kind of snow that wouldn't have done anything. Instead, we got like 1.5 feet of really wet snow. It was a pretty remarkable event. And of interest, this, if you remember this, this was a really lame winter otherwise. 2015-16 was mild and boring other than this big snowstorm. Like I think in Valpo, we got maybe 30 inches that winter, and more than half of it came in this one day. So it's pretty neat. So that's the kind of system that comes through from time to time, and it snows, and then it's not even that cold, and the following week might be above freezing, et cetera, et cetera. Then we also get lake effect snow. And in essence, with lake effect snow, it can be complicated, but in essence, cold air from our Canadian friends passes over the Great Lakes, and the Great Lakes have plenty of open water typically through much of the winter. And so you get a pretty big heat and moisture exchange. You get evaporation from the lake surface. So that's adding water vapor that you need for precipitation. And then importantly, it destabilizes the air mass. Having cold air spill over a much warmer surface helps generate some vertical motion. And so, of course, throughout the winter, the lake is often warmer than the air upstream. But in specialized circumstances where you get some pretty strong flow of that air over, say, Lake Michigan, then you generate bands of snow from this process. This is a National Weather Service graphic, but over on the right, this is from an old classic journal article. And if you look at the top, you see some typical kind of cloud band structures that you would get during lake effect snow events. So the most typical event with Lake Michigan affects southwest lower Michigan, and then like towards South Bend and sometimes LaPorte, if you're familiar with the Indiana geography, but not really Valpo. So when you get west or northwest winds with these cold air outbreaks, you get these multiple wind parallel bands, mostly affecting southwest Michigan, and as the winds become more northerly towards South Bend and even LaPorte. But we really never get in Valpo snow from that kind of event. But instead, if you look at category number 3, if we get a due north wind, more or less, which is much less common, so this doesn't happen nearly as often, unfortunately, then you get a really focused dominant band that comes right through the middle of the lake. And then it doesn't always set place right in Valpo when it comes ashore, sadly. But sometimes it does. We're a pretty good location for that. So these events aren't as frequent, but when they happen, we can get shellacked here in Valpo. Whereas in, say, Southwest Michigan, it just snows far more often from lake effect systems. Here is a radar image from one of the most spectacular lake effect events that impacted good old Valpo from February of 2009, February 3rd, 4th of 2009. This very narrow, intense band on this map, it doesn't really, it's radar composite, it doesn't really look like much, but this was very, very intense snowfall. And in Valpo, we had about 2 feet, which was quite remarkable. It had snowed pretty intensely for a few hours in the afternoon, shifted east, and pretty much I figured it was over. And then that night, it actually rotated back over us a little bit for several hours, and that was a remarkable snow, one of the biggest lake effect events in Valpo that I'm aware of. So pretty neat. We don't get those that often here because, again, usually with cold air outbreaks, the winds are northwest, and so that takes the snow east of us, sadly. Okay, so to broaden this a little bit, we get snowstorms like that every winter, sometimes lake effect snow, and especially east of here. And migrating mid-latitude cyclones. We get those every winter. Some winters are, have a little bit milder pattern or a little bit colder pattern, so that affects how much of this stuff falls as snow versus rain. But pretty much in a typical winter, if you think about it, at this latitude, you get a cold week with some snow, and then it warms up and most of the snow melts, and then it gets cold again. That's very, very typical. You go up to Minnesota, the snow stays on the ground a lot longer. You go to Kentucky and, you don't get much snow at all, a lot of years anyway. But what explains the other periods, which will be our focus now, in which we get locked into kind of a cold pattern and it stays cold and snowy for several weeks, really a month or even sometimes a season, in a more unusual case. So what kind of explains that? And for that, we back up now to look at some larger scale patterns. So what's being plotted here has some complicated aspects that aren't all that important. But if you look at this map, so centered over North America and the Great Lakes, but then showing importantly the adjacent Pacific and Atlantic sectors and some of the Arctic. If you look at this and just think of these colors as representing temperature, then you pretty much get the big picture. So this is showing a map effectively of cold, snowy Decembers in the Lake Michigan region, and then the pattern associated with that. And so this is a pattern that fosters cold, snowy conditions in, say, Northwest Indiana or the Lake Michigan basin. It's not just cold right nearby. Instead, it's cold centered actually a little bit west of us typically, and then through a good chunk, though not all, of the CONUS in the most classic version. But then the reason I'm showing this is so that you can see the broader view. If you look at this, when we get a month, December in this example, but January and February would look very similar. When we get a month that is cold and also snowy in this part of the world, look at Alaska and Greenland and the Arctic more broadly. It's warmer than average there. These are all with respect to average. It doesn't mean Greenland is suddenly, 75 degrees in January, just warmer than average, well above average, in fact. So if you want it cold here, you want it warm other places in a particular configuration. We're not always cold when those places are warm, just to make life interesting. But when we are cold, it is almost always warmer than average these other places. Now, how do we kind of put that together to understand it as a system? Well, first we're going to back up a little bit. So I'll bet a lot of you at some point in your life took some kind of meteorology class because you're interested enough as alumni to sign into some of this. And I see some program alumni here on the list, but the others, you probably took a meteorology class at some point, or if not, you watched the Weather Channel. Or if not, you saw the evening news and have heard of some of these things. So the polar jet stream we teach in any basic meteorology class, and you learn about it on the Weather Channel and on the nightly news as well if you've got a good weathercaster and TV meteorologist. And the polar jet stream is really important in the winter months especially. Also spring, but really winter especially. And the polar jet separates on the polar side from kind of, mid-latitude milder air on the other side. Not necessarily, steaming hot, but milder. So this is really kind of at the boundary, the equatorward boundary of the Arctic air, broadly speaking. The polar jet stream occurs actually in response to temperature contrasts. So there's a bit of a chicken and egg here in that seeing where the jet is tells me where the boundary is between warm and cold air, but it's actually the locations of the cold and warm air that generate the jet itself. So the jet in this example is running from a textbook, is running right through here. It tells me in that instance that it's a lot colder here than it is right on the other side in that instance. Otherwise, you wouldn't have a polar jet right there. So that's pretty cool. Now, the jet stream varies by season, right? It's stronger in the winter when these temperature contrasts are greater. And day to day, week to week, it meanders about. The subtropical jet, which we're not talking about at all, please ignore that, other than the one quick thing I'm going to say, the subtropical jet doesn't meander nearly as much. But the polar jet moves all over the place. Meanders here, there, and everywhere. Usually, if you don't like where it is, just wait a handful of days and it will have moved. So there you have it. But sometimes it gets kind of locked into a certain pattern, and then that locks you into a really mild month or season or a really cold month or season. So this is often described in terms of the polar vortex. So the language of the polar vortex had been around for a really long time, but it entered the public lexicon, several winters ago. Their very impressive, epic 2013-14 winter, which was quite hardy, and in much of the United States. And so that's when really this language entered the public lexicon. But scientists in some ways had referred to this for a long time. How is it measured? Well, there's another term called the Arctic oscillation, which is a way of measuring and defining this. So polar vortex is kind of the concept that's easy to visualize, and then the Arctic oscillation is really sort of an objective measurement of it, an index. So what's a polar vortex? Well, it's really not that complicated. In essence, it's just a description of that polar jet as a kind of a system, kind of looking at how it behaves as it goes all the way around the world. If we're just looking at the Midwest and Canada and seeing where the jet lies, that's great for weather over a couple of days to understand that. But if we want to take a broader view, you can kind of look at the jet ringing around the world in the northern hemisphere winter, and then think of that as the polar vortex. So the polar vortex, of course, has a full spectrum of behavior, but it can be characterized generally as strong or weak. And a strong polar vortex isn't what you might think. So having experienced, polar vortex winters, when we get cold air outbreaks, it seems very dramatic because that's when it's being mentioned. But actually, when the polar vortex is strong, our weather is boring, 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 mild and dull when the polar vortex is strong, because we live in mid-latitudes. And when our wintertime polar vortex is strong, you get a really strong jet stream, but it is anchored at high latitudes. So when the polar vortex is really strong, it's quite cold in the Arctic, colder than average. So wintertime Arctic, colder than average, is really cold. While mid-latitudes are mild because the jet's up there. And sometimes this locks into place where for weeks at a time or longer, it kind of looks like this. Doesn't mean you don't get any weather, but it stays mostly like this with the jet kind of anchored to our north. When the polar vortex is weaker, then the jet isn't as strong, but it has a greater influence in mid-latitudes because it meanders around. And you get these really nice looking waves that almost look like little sine waves. And so when you have a weaker than average polar jet, you get the irony that the Arctic is actually milder than average, but you get some good cold air into mid-latitudes, which seems odd, but it's true. So when the polar vortex is weak, you get a more meandering jet stream, but that doesn't mean it's cold everywhere in mid latitudes, because when you get this ridge trough pattern, some regions will be mild while other regions are cold. So in this particular example from a nice NOAA graphic, it would actually be mild here in the Central Plains in this particular example, but cold in the Eastern Great Lakes, and so on and so on. So let's take a look at February as an example, because February, as you may recall, was memorable. You might also recall that January wasn't anything like February, and that March, pretty much as soon as by the time we got to March 1st, the whole pattern was different as well. But February was memorable, especially the first 3 weeks or so of February. So here's February 2021. And these aren't exactly temperature in this map on the left, but you can think of them as mapping the temperature. And the northern hemisphere pattern looks kind of cool. Importantly, you have warmth in much of the Arctic. That is associated with a weaker than average polar vortex. So a weaker than average polar vortex. Warmth in the Arctic more or less tells you you have a weaker than average polar vortex. And the Arctic oscillation is a way of measuring this. And the Arctic oscillation value was about -1 and change. The units for this, by the way, are standard deviation from the mean. So -1 may not sound like much, but that's actually pretty impressively negative. Not off the charts, but it's a good negative value. If you then look at the details, so in this particular instance, we got the warmth in the Arctic. And then if you look through mid latitudes, it's not cold everywhere. Instead, it goes back and forth, like in this hypothetical image over here on the right. So you have a well-defined mid-latitude trough ridge pattern. And so we got a ridge in the Pacific where it was warm, and then nice troughing for much of the United States, where, as you may recall, it was not warm. It was impressively cold for February in much of the United States, and then kind of back and forth. Ridge, trough, ridge that kind of looks a little funky there, trough, ridge, trough, etc. Kind of a neat little pattern going around in mid latitudes with warmth in the Arctic. And then on the lower right, there's a nice NOAA graphic showing surface temperature departures from average, and you can really see that cold air that went all the way rather infamously to Texas. And those are pretty big temperature anomalies. So here's a quick cold month sampler where you see some of the other randomly chosen, more or less, cold months in this part of the country. And if you look, you see some differences. They do not all look identical by any stretch of the imagination, but you see some commonalities. So one commonality is the obvious one that you see cold colors over the Great Lakes, which that makes sense because I wouldn't have chosen them otherwise. I'm choosing cold month sampler for here. So that had to be the case. But if you look more broadly, you see plenty of differences instance to instance. But one commonality is that you in Greenland and parts of Siberia, etc. But it's not
Professor Clark,
always.
could you repeat that sentence? You cut out for just a moment.
Oh, okay. Just the last little bit.
Yeah, just like the last sentence or so.
Okay, so the part that's consistent here is that in addition to the cold in, say, Indiana, which was part of choosing these months, you have warmth in the Arctic. So not all of them look the same. Some look more impressive and exactly where the warm bubble is relative to average. is not always in the same exact place, of course, but you have this commonality where it's warmer than average in the Arctic, consistent with a weaker than average polar vortex. So you get a meandering jet stream, a meandering jet stream. Okay, this January 78 one looks a little different, but the others all pretty much have that same feature. And some of you, depending on your age, may remember some of these impressive months if you lived around here. January 2014, of course, was classic. December 2000, this map doesn't look as impressive, but actually Valpo got a ton of snow and cold that month. And these classics from the late 70s, 3 years in a row, in fact, pretty impressive. So a couple of kind of guiding questions. Do these unusual months tell you much about the following month? And really, it's not much. The indexes that we can use to quantify these patterns are almost independent month to month. If you're a stats person, the serial correlation is almost zero. It's just not quite zero, but very close. So not very much, asymptotically approaching nothing, a little better than nothing, but not much information, which makes seasonal prediction more challenging, by the way, because sometimes these patterns lock in for multiple months, but you cannot count on that. So, if next December, it's like Santa Claus is coming to town and you got lots of snow and cold, you can't assume it's going to be like that, as you're planning your January skiing vacation, because systematically we just don't find something like that. The other question, does a weak polar vortex guarantee wintry conditions? And that is another no. Nope. Because in the examples we've looked at, the polar vortex was weak and the trough ridge mid-latitude pattern put a nice impressive trough that locked into place for a month more or less in the Great Lakes. But that's not destiny. It doesn't always get placed there. So we can actually see this by simply backing up the clock. The polar vortex was also weak in December and January this winter, but our weather was mild and boring. There was a trough ridge pattern, but the trough wasn't in the central United States. So, and in fact, our measurement of that pattern, that Arctic oscillation, was actually even lower. So the polar vortex was even weaker in December and January, but our weather was materially, dramatically different. The reason I mention this is because when the polar vortex and these kind of things get talked about in the United States, when it's newsworthy is when cold air is either occurring or expected, it's coming right at us the following week. And so that could give the impression that whenever we go into this kind of weak polar vortex, it's destiny that we're going to get cold here, but it isn't. Sometimes we're in the ridge instead of the trough. So instead, December to January, the cold was in some areas adjacent to Europe, and then off here in parts of Northeast Asia and towards parts of Alaska, instead of here in Valpo, which was mild and boring. And then you can see the temperature plots there. Okay. Let's see. So when was the last winter with a strong polar vortex? Well, it was last year. So last winter, the winter 1920 actually had a very strong polar vortex. So this index value was 2, summed through those core winter months. And then you had colder than average conditions broadly in the Arctic. And then most of mid-latitudes were quite warm. And winter here was pretty dull. I mean, we did get some decent snowstorms from time to time, but nothing that persisted. It's pretty mild and dull in most of mid-latitudes last winter. Okay, a few other things, and I'll open up to questions. So this is sort of a broad brush of the largest scale kind of pattern that influences our weather, really, kind of where the jet is lining up and whether it's really meandering or not. But there are some other things that we cover in our meteorology coursework that are also patterns that affect North America a lot. And they're actually centered in the oceans. There's one centered in the Atlantic, North Atlantic, and another one centered in the North Pacific. And they are co-located with subpolar lows, if you've ever heard of those. Those that are meteorology students might remember that. And those influence our weather a lot. I don't have time to get into those today, but those have a big influence as well. And you probably also heard of El Nino Southern Oscillation. When we get a big El Nino, it destroys our winter here. Pretty much, you just get a lot of balmy air blown into Western Canada, and then most of our El Nino winters are pretty boring. And I didn't have time to get into that today, but the neatest thing about, say, El Nino years is you usually know ahead of time that that's going to happen, whereas all this other stuff, you can't really predict it with any competence, really, months in advance. Whereas a winter that has an El Nino brewing, it's usually pretty obvious, October, November. So that gives some skill to those sorts of things that are otherwise kind of complicated. So I will wrap it up there. I'll say thank you, and then I'll entertain any questions.
Well, thank you so much. That was wonderful. I haven't seen any questions come into the chat. So if you have a question at this time, go ahead and unmute and ask.
So Stephanie, I think you told me before you got a question ahead of time about snow in Southwest Michigan.
Yeah, so we had a question, I think it was from Jonathan there actually, about the departure from normal in certain parts of the country, particularly Grand Rapids. Was that you, Jonathan?
Yes, that was me.
Yeah, so go ahead if you want to. Yeah, go ahead.
Yeah, I mean, some of those things can get kind of fluky in the sense of, whether one of those bigger systems that comes through really hammers a particular place or not. But largely, it's been that this hasn't been a great lake effect snow year. And in Southwest Michigan, you got to get typically some pretty frequent lake effect snow events in order to really get an impressive seasonal snowfall total. So you see it in South Bend as well, though it's less dramatic there. They're running, 10-ish inches below average, where Chicago is running above average. But in Southwest Michigan, their climatological snowfall is a lot higher. They get a lot of lake effect snow, but a lot of them are, modest snowfall amounts, but with a lot of frequency. And this winter, almost all the snow, or lion's share of it, came, within like a 3 to 4 week period. And so there just weren't enough days of snowfall for Southwest Michigan to get what would be impressive snowfall for Southwest Michigan. Despite how cold February was, there just weren't enough days below freezing for them to have an impressive snowfall year, unless they'd gotten a really epic lake effect event. One really big event can make up a lot of ground. But in general, it's not quite as surprising, just because the cold air wasn't in place long enough, even though it was very impressive in February. Whereas, relative to average, Chicago's had a much better winter than, Southwest Michigan or South Bend have had, because they've had almost as much snow as some of those places. Got hit harder with some of the systems that came through.
Yeah, I'll ask another question too. There's a lot of meteorologists and weather enthusiasts on this call that know that we've had a few active severe weather days so far this month, and are poised to have another one tomorrow as well. Does any of the patterns, do any of the patterns that you saw this winter regarding that weak polar jet, regardless of whether or not it was cold here or in certain areas, does that inform any of what we might be seeing with those severe weather patterns as we enter into spring?
Not directly. What's what's more relevant there is we're in a La Nina, and La Ninas don't actually affect our weather very much here systematically in the Western Great Lakes. Some parts of the US have a bigger sensitivity, but we don't. But in the Southern Plains, springs with La Ninas have a greater severe weather risk in general, down, towards Oklahoma, Texas, et cetera. So there, it didn't guarantee that they were going to have an active severe weather season that's sort of just getting started. But the risk of having an elevated severe weather season is a little bit greater because of the La Nina. Actually, I'm not a severe weather buff. Some of the alums watching might have a better answer actually for that if they want to chime in.
I'm still muted, sorry. Maybe give you a second to think about that, but there's a great question in the chat from Katie, who asks, what causes the sudden stratospheric warming events over the poles?
Hi, Craig.
I find that hello, and I have always found, Katie, honestly, I've always found it incredibly confusing. So it has to do with wave propagation that I just don't fully get. And because it's not so the part that sort of relates is that if you're in kind of a boring weather regime in the winter, a predicate that sometimes happens that changes the pattern dramatically is that you blow up a big enough storm somewhere in mid-latitudes, or even starting in the tropics or some of the oceans, and you get a big warm push into the Arctic, and then you reset the entire circulation over a period of weeks after a warm advection episode into the Arctic. And even in winter, you can get well above freezing air spilling over the Greenland ice sheet, which is just sort of bizarre to imagine, but it happens. The stratospheric piece I've always found confusing, honestly, because of the wave propagation in the vertical. So yeah, I don't really have a very good answer for you there, other than the fact that it does give pretty good lead time. When these events happen, and this one was pretty well publicized on message boards and map discussions and whatnot, it increased the odds of that pattern occurring, but it didn't necessarily mean the cold air was going to come here. This often happens a few weeks after one of those events, but it doesn't always happen here. But in this instance, the long range models very quickly had it right. I mean, the GFS, Global Forecast System model, in the Euro, many days out, had this Arctic blast pretty much, perfectly simulated in the broad essence of that. The challenge is that there were multiple times earlier this winter in which the GFS also had it getting Arctic in let's see, first early December, and then mid-December, and then late December, and it didn't happen those times. So there's always uncertainty, but it really nailed that.
It was such a letdown in December.
It sure was. It sure was.
Oh, thanks, Craig.
Thanks.
We've got a couple more questions in the chat. I'm going to ask them out of order just because of the way they relate to what's been said. So there is a question, is the trend in the Arctic show continued warming?
Yeah, the Arctic amplification is quite remarkable. The Arctic of the Northern Hemisphere is warming more than any other region on Earth, and it's continuing largely unabated. The reasons for that are largely that feedback mechanisms are stronger there. Greenland's a lot smaller than Antarctica. And you get some pretty dramatic heat exchanges as mid-latitude systems come through in the winter between mid-latitudes and high latitudes. So with decreasing sea ice and snow cover to some extent, but mostly sea ice reductions in the Arctic. You're getting a lot of rapid warming there. There is some feedback onto all of this. In idealized model simulations, you get a weakened polar vortex in some simulations, but that's when you're isolating one thing as opposed to ocean warming and other factors. So it's still kind of hotly debated whether we will really see a systematic weakening of the polar vortex in wintertime in the coming decades. It's a little bit complicated. So far, in terms of the data, the way that we measure that circulation is through the Arctic Oscillation and another variation called the NAO, and those don't reflect a systematic weakening. Actually, for several decades, there was a strengthening. So the jury is out on that. I think the conceptual understanding or the conceptual theory makes some sense about a weakened polar vortex, but the details are complicated. I think it'll be a long time before we really know. Even if that happens, it doesn't mean that our winters would get colder, for example, because the cold pool each winter is shrinking. So in order to stay really cold here, we have to maximize the pattern more and more and more to really rack up an impressive month or season as time goes on. So it's really hard to countervail that.
Yeah, Margaret has a question about small scale melting. So we talked a little bit about Arctic sea ice, but Margaret is asking about lake ice and how it seems to disappear so quickly when we have any kind of warming after a long, an extended cold event. Could you talk a little bit about why that happens, how it happens, and why it happens so quickly?
Yeah, very good question. A lot of it depends on how thick the ice is. So if we get a really cold winter where the cold persists for a long time, then you get thicker ice and the water below is, gets really, really close to freezing. So you're kind of the warmth of that reservoir is pretty limited. So it can take longer to start getting the melting. Even, so like this year, as cold as February was, I doubt the ice really got that thick because there just weren't that many weeks in a row with sub-freezing high temperatures. I mean, that 3-week period was truly as epic as any 3 weeks I've ever actually experienced in terms of cold weather. Don't get me wrong, but 3 weeks is not 10 weeks. And this part of the country has had some epic winters with, 60 out of 70 days below freezing in a row, which would affect lakes much more. The lake ice in the Great Lakes is decreasing over time, though in 2013-14, at least in the satellite era, going back to 79, they actually hit a new record in some of the lakes on the other end of the scale. But the lake ice has been generally shrinking. One of the cool things about the lakes is if you start off the winter season with really mild lakes because the summer and fall were warm, then initially if you get an early season cold blast, that can really aid the lake effect snows and make them that much more impressive. But it doesn't take very many cold air blasts before the lake surface temperature cools off really quickly. So it doesn't last that long.
Yeah, thank you for that question, Margaret. So 2 more questions about lake effect snow.
Okay.
And one actually, and 2 questions about lake effect. So one is about snow. How far generally do lake effect snow, you showed the 4 different kind of types that's set up. How far do those generally extend? So Alicia asks, I live about 60 miles south of Lake Erie. They get a lot more snow than we do. So asking about why that happens. And then we also had a question about, does the lake affect rain events like it does snow events?
I'll take the second question. I'm backing up to get to a nice graphic here. There is lake effect rain. And we get lake effect rain in the fall mostly. And basically it's just like lake effect snow, but it's a lot less dramatic. The precipitation that falls from lake effect rain tends not to seem to add up to very much because there's actually not that much water mass. So with lake effect snow, it's very light, puffy snow. And so you could get a foot of it or 2 feet of it, but it's typically not that much actual water most of the time. It's very light, fluffy snow. So when you get lake effect rain and it's in that liquid form, the actual rainfall amount is not that much. I mean, you might get rain showers through a whole day in the fall, but it adds up to a 1/4 inch or something like that. So it doesn't ostensibly seem that impressive. But we do get lake effect rain, especially in the fall. And one thing that's always interested me, anecdotally at least, is that when there's lake effect rain in the fall, Valpo is much more likely to get that than we are the lake effect snow in the winter. There's a greater tendency for those events to have more of a northerly wind than a west-northwest wind. So we're in a better position for that. I could speculate about why I think that is, but I haven't really looked into it. So, but we do get lake effect rain in the fall. Usually it's kind of a shower and then it stops, and another shower and then it stops, and one of those classic October days where it's been 75 and then suddenly it's 40 with driving drizzle as you go across the campus. The other question is a very important one, in part because it affects the snowfall amounts tremendously. So how far the lake effect bands will penetrate inland depends on the wind speed largely. So if you get strong winds, then the bands will spread inland much further, so potentially affecting a greater population. But also there's sort of there's only so much water vapor making snow. So there's kind of, in a weird way, a conservation of snow. If you spread it out over a much greater distance, you're not going to get as much in any one place. So I'll give you an example. There have been times in which it looked like South Bend, say, was going to get a really epic lake effect event, several hours of moderate to heavy snowfall with kind of a dominant band setting up over them. And it could be a really big event, but the winds were going to be quite strong. And in a few instances, the winds were actually so strong that the band stretched just seemingly forever, all the way to Fort Wayne. And you literally are just dividing the total amount of snow by too much surface area. And so you just don't get as much snow in any one place. But when the winds are strong, the bands can penetrate a lot further. With the eastern lakes, Erie and Ontario, it's interesting there because the heavy snow can, in fact, in those very narrow, intense bands, the heavy snow can shift inland a great distance, but it's almost always just east of the lake because they have a dominant west wind. And so imagine this was Lake Erie, which obviously it isn't. And then your snow would be extending well east of the lake out kind of this way. And it doesn't typically get that far south of Erie or on Ontario. Because most of their big events have a big westerly component to the wind. So it takes it well to the east.
Yeah, interesting. These are all great questions, everyone. Do we have any, we have time for maybe one more, if anyone has any lingering questions. I have one that, Katie has one. What's your favorite snowflake shape? That might be a joke, Katie, but I'll read it anyway.
I don't think so. Classic dendrites. Got to go the classic iconic dendrites. The Hollywood looking snow, except in real life. That's the magic. But they're all fine. They're all fine. I can tell you the snow I didn't like was the sleety snow pelting us yesterday with the high winds. I did not enjoy that snow, but all the other snow is good.
Yeah, Jonathan mentioned, he made a remark about, the water content of snow is inversely proportional to your eagerness to shovel the water.
That's right. That's exactly right.
That one of those big February snows that we had in the Valparaiso area was a really wet snow, really heavy. Could you talk, you talked a little bit about how lake effect snow generally light and fluffy. What are some of the factors that enter into the type of snowfall that we receive, the character of the snow?
A lot of it is how much water vapor there is. So with a mid-latitude system, that's really dependent on the moisture from the Gulf of Mexico. So how much is feeding into the storm? And then there are temperature effects. So how cold the cloud layer is. But then that's also going to depend on how much vertical motion is in the system. Like that example that I showed with a really wet February snow from, what was that, 2016. In that case, if there hadn't been a lot of vertical motion, I think it would have been more like a sleety snow rain mix. It just wasn't very cold enough. If anyone remembers their cloud processes, if you hadn't had pretty good lift, it would have been difficult to get enough ice nuclei with that temperature profile. But with good lift, you get to where it is cold enough. If it's too cold, then you don't get those classic dendrites. The snow will be, the snow has a different kind of structure. You've all experienced that, where it's kind of like beady snow, and it can accumulate if you got enough of it, and it snows long enough. I think it's nice for skiers or sledders or whatever, but it's not the kind of that Hollywood looking dendrite snow. When you kind of have temperatures cold enough to get good dendrites, but not so cold that there's not as much water vapor, that's where you can really get a lot of accumulation, and that's what happens with that fluffy lake effect snow. As it gets closer and closer to freezing, the snow gets wetter and wetter, which means it can have a really big impact on snow removal and other kind of experiences with the snow. But it means you need that much more water to get your inches of snow.
Yeah. Well, we are just out of time. So thank you again, Dr. Clark, for joining us. And thank you for all of you.
Thank you. It was fun.
Yeah, we've all enjoyed your expertise this evening on Alumni Experts. To our guests, we have some other exciting virtual events coming up, including a study abroad alumni happy hour and info session this Friday at 5:30 Central. So if you studied abroad at Valpo and you want to catch up on the program, please join us. You can register for that event at alumni.valpo.edu/abroad319, as in the date 319. To see upcoming and past Valpo alumni events, you can visit alumni.valpo.edu/events. And to see recordings, including of tonight's event, you can visit our Valpo alumni YouTube channel. And I'll get that up as soon as I can. So if you missed any portion of tonight's events, check back to our YouTube channel and you can see the recording. We hope you'll also follow us on social media to stay connected to exciting news and events. So that's at Valpo Alumni on Twitter and Instagram, and Valparaiso University Alumni on Facebook. Thank you all again, and have a great rest of your evening.
Thank you.